So, in the last class, we had a brief discussion on crystal systems and Bravais lattices. And one important point that emerged from that class was that the crystal systems, which are usually defined in terms of their lattice parameters A, B and C and their angles alpha, beta and gamma, is not a correct way of defining the crystal systems. So, for instance, if we say it is a cubic crystal, we take a cubic unit cell and we say that the parameters should be A equal to B equal to C and alpha is equal to beta is equal to gamma is equal to 90 degrees. So, as we progress in this course, I would like to remove this misconception and bring in symmetry, that symmetry is the basis for these crystal systems and not the relationship or the constraints on the parameters. In fact, one can also say that you can choose any kind of unit cell. We have already seen that you can have any type of unit cells for any of those lattices, whether it is you can even for face centered cubic, we saw that we can choose a primitive unit cell, but even if you choose a primitive unit cell, it will still belong to the cubic system. Now, in this lecture, I would like to look at some very common crystal structures and the way to define them in terms of the rules of crystallography. So, let us take a very simple structure first. Let us take a structure crystal of iron at room temperature. Iron is a body centered cubic structure. So, what this means is that its lattice is body centered cubic. So, if I take a conventional unit cell from the Bravais lattice for the BCC lattice, then I will have lattice points at the corners and I will have a lattice point in the body centered position. Now, in this lattice, I put iron atoms now. So, I put an iron atom at every lattice point. So, I form this body centered cubic structure for iron. Let me consider another example. Of face centered cubic structure, let us say for copper. So, if this is going to be a FCC lattice, then I will have lattice points this time at the corners and I will have lattice points in the centers of all the 6 faces. And I can put a copper atom whose center coincides with the lattice points. So, I put copper atoms at all the corners, then I put it at the face centers, forming a face centered cubic structure for copper. So, here what have we done? So, we should realize that go back couple of lectures back, we have defined a crystal a relationship for crystal in terms of lattice plus motif. So, let us look at this relationship and how it applies to this structure. So, in the first case, the body centered cubic structure for iron, what have we done? What is the lattice? Well, the lattice is BCC lattice plus what is the motif? Motif is one iron atom at coordinates 0, 0, 0. So, now remember, going back maybe 2 lectures back, we said that crystal is equal to lattice plus motif is a vector addition. So, essentially what we are going to do is we add up this vector, or another way you can look at it is that we can add the motif vector or the motif location from every lattice point. So, I go to every lattice point in the unit cell and I put an iron atom at the location 0, 0, 0. Now, obviously, that simply is a vector on the lattice point itself, and that is how the iron atom comes out in this way. In a same way, if I come to now the copper structure, so here I have a FCC lattice plus one copper atom at 0, 0, 0. Same thing, that from every lattice point I draw a vector, taking that lattice point as the origin, I draw a vector to 0, 0, 0, which means that the atom will fall on the lattice point, or the atom center will coincide with the lattice point. Now, let us take another structure. Let us take the structure of, let us say, cesium chloride. Let us see how that structure looks like first, and then we will try to figure out what is the lattice for that structure. It is again a cubic structure, so it belongs to the cubic crystal system. And let me put cesium ions and chlorine ions in their appropriate locations. So, the chlorine ions go at the corners, and the smaller cesium ion I put it at the body centered position. Now, let us look at the structure and try to figure out what is its lattice. Very often, just because we see atoms at the corners and at the body centered position in a cube, we assume it is a body centered cubic structure, which is incorrect. So, let me first say that, is it BCC lattice? It is incorrect. So, how is it incorrect? Let us also look at that. Remember, all crystal structures have to be based on one of the Bravais lattices. Now, which means that if a lattice has a certain translation symmetry, the same translation symmetry should exist in the crystal with atoms in it. Now, a body centered cubic lattice. So, if I were to draw a body centered cubic lattice separately, and let us look at what translation symmetry is permitted. So, let us say this is A, B and C, and the translation symmetry that I can have is take from any lattice point. So, let us say these are my, let me put these body centered cubic lattice points. So, what are the translations permissible? Well, there is a translation obviously along A, along B, along C of the magnitude A, B and C in fact. So, in fact A equal to B equal to C would be the case for this cubic crystal, but this is also a permissible translation, and this vector would be, in this case, would be A by 2, B by 2, C by 2. It joins from one lattice point to another lattice point, and this is a perfectly correct lattice as far as translation symmetry is concerned. So, here we have some translation symmetry, which would be some factors multiplied into the vectors A, vector B and vector C. Some of them are going to be integers and some of them are going to be factor which brings the lattice point to the body centered position in this case. Now, coming back to this, if I apply this translation symmetry A by 2, B by 2, C by 2, this will take me, a chlorine ion will be taken to the position of cesium plus ion, which means symmetry is violated. So, therefore, this cannot be a body centered cubic structure. So, then what is this structure? How about if we consider a different lattice? How about if I consider the lattice points to be only at the corners? So, I have now lattice points only at the corners. If I put a lattice point where the cesium plus ion is, I will have to put, if we assume this is a body centered cubic structure, but then we have seen this violates the translation symmetry, because chlorine ion displays to a position of cesium plus ion. So, the translation symmetry is not maintained. However, if I take this with the lattice points only at the corners, it works perfectly fine. So, this actually becomes a simple cubic structure. So, my lattice is going to be simple cubic lattice but then what will be the motif, because I have to have both the cesium ions and the chlorine ions. So, therefore, this motif is going to consist of two atoms and not one atom. In the previous case for iron and copper, we had a motif with only one atom. So, where is my chlorine ion? Therefore, let us figure out what is the motif. So, one chlorine ion, since the chlorine ions are all located at the lattice points, its position is going to be 0, 0, 0. Then I have a cesium ion, its location would be half, half, half. So, I am using this system of fractional coordinates, not A by 2, B by 2, C by 2, but just half, half, half. So, in crystal space, what we do is we take A, B, C vectors as basically unit vectors along the x direction, y direction and z direction, and therefore, we just need to specify them by their fractional coordinates within the unit cell. So, simple cubic lattice, and this becomes my motif of two atoms. So, this is another thing that a lot of sources are there where mistakenly such a structure is called as a body centered cubic structure. In fact, it should be called only as a simple cubic structure. It has the cubic symmetry and its lattice is that of the simple cubic. Now, consider one more structure which is of sodium chloride. Now, let me first draw the structure and then we will try to figure out what is its lattice, what is its Bravais lattice and what is its motif. Again, sodium chloride structure is also belongs to the cubic crystal system, and let me put now the sodium ions and the chlorine ions at their specific locations in this. So, the chlorine ions go at the corners and at all the face centers. So, these are chlorine ions. The sodium ions go to the center of all the edges and one sodium ion will go at the body centered position, which I will just shade it to separate this out, that the shaded sodium ion is at the body centered position. So, there are a lot of atoms in this. So, now how do I describe this structure? What is its Bravais lattice and what is its motif? So, very often such a structure is described as two interpenetrating. So, let me just write this down, that often the structure defined as interpenetrating FCC. In fact, I should say two interpenetrating FCC lattice, one containing the chlorine ions and the other one supposedly containing the sodium ions. So, this is a somewhat of a problematic description, and I would like to avoid this way of describing the structure of sodium chloride. First of all, there can only be one lattice for any crystal structure, however complicated the structure may be, how many number of atoms that structure may have. So, by saying two interpenetrating FCC lattice, we are saying there are now a lot of lattice points all around, but lattice points cannot be there for the same reason that the lattice point could not have been there for the cesium ion in the cesium chloride crystal. In the same way, I can say that I can put the lattice points at all the chlorine ions, but not on the sodium ion here. So, if I put the lattice points, so I will put the lattice points in this structure at the corners. In fact, there should have been a sodium ion here as well. Then I will put the lattice points at all the face centers. Essentially, what I am saying is that this is a FCC lattice. But then, in order to describe this structure, I now need a motif. The same way as we did for cesium chloride, let us look at it. How many chlorine ions are there in this unit cell? Well, if you consider the corners, remember each corner gives us 1/8 contribution to the unit cell. So, there is one chlorine ion coming from the corners, half a contribution from each of the 6 face centered, which would mean 6 into half, 3 chlorine ions. So, 3 plus 1, 4. So, I have 4 chlorine ions in this per unit cell. Same way, you will notice that the center edges, the sodium ion is shared between 4 unit cells. So, 1/4 of a contribution, and there are 12 edges. So, that would bring us to only 3 sodium ions from the edges and 1 sodium ion from the body centered ion that is there, which is completely inside the structure. Therefore, I have effectively 4 sodium ions and 4 chlorine ions in this unit cell. But then I know that this is an FCC lattice, so I have 4 lattice points per unit cell as well. So, what I can do now is, if I say 1 chlorine ions will go at location 0, 0, 0. What that means is that all the sodium ions will go to all the lattice points of the unit cell. So, therefore, they will go to the corners and they will go to into the face centered. What about now at all the lattice points? Their centers will correspond to the lattice points. Now, how about the sodium ions? Now, sodium ions are also in the equal number. Their stoichiometry is sodium chloride NaCl. So, one sodium ion at, how do I put it? Let us take one specific one. Let us say, how about taking this sodium ion? What is its coordinates? If my coordinate system is A, B, C in this way, so it is A by 2. So, along A half the way and 0 along B and 0 along C. Therefore, its coordinate actually, if I look at absolute coordinate, it is A by 2, 0, 0. If I then say that I will remove the A and just take the fractional part, then this sodium ion is in the motif. So, this is my motif. So, again 2 atom motif. So, this is a 2 atom motif with chlorine ion at 0, 0, 0 and sodium ion at half 0, 0. So, what will this do? At every lattice point you go. So, for example, if I come to a specific lattice point, let us say I come at the lattice point, if this is my origin. So, from this lattice point I draw a vector half 0, 0. Like this, if I draw a vector half 0, 0, I come to the sodium ion and it will populate the unit cell with the correct locations for sodium ions and chlorine ions. So, I will again reiterate that this is what we will always consider, that crystal can be related to a lattice plus a motif. So, sodium chloride has a face centered cubic lattice with a motif of one chlorine ion, one sodium ion at the specific locations. There is one more structure I could consider. Let us take the structure of diamond. Now, in this structure basically we have only carbon atoms. So, let me put the carbon atoms. Carbon atoms will go at the corners. This is also a cubic cell. And the carbon atoms will go at the face centered location. There are another 4 carbon atoms will also go inside the unit cell, which would be located on the body diagonals. So, for example, if I look at some, let me draw the body diagonals first. Body diagonals means you are joining the opposite corners of the cube. So, there is a carbon atom which will go out here 1/4 along this particular body diagonal. Another carbon atom would come here 1/4 from this particular vertex. Similarly, there will be a carbon atom that will come here and there will be a carbon atom which would be somewhere here. So, this is again, if you look at it, first of all the red atoms, I mean the red and the green, they are all carbon atoms, but the red ones are lying on the corners and the face centered positions. The green ones are lying on the body diagonal. So, if you look at the number of carbon atoms, one will find that there are 8 carbon atoms per unit cell. Now, what is its lattice? So, its lattice is face centered cubic, which means the lattice points can only be at the corners and at the face centered location. So, therefore, this crystal or the diamond structure can be described by an FCC lattice plus a motif of 2 carbon atoms. One carbon atom at 0, 0, 0, which means they will just go on the lattice positions. The second carbon atom, so if I take this particular atom here, this is 1/4 along the body diagonal joining this vertex to this opposite vertex. What will be its fractional coordinates in terms of A, B and C? Its fractional coordinates are going to be, since it is 1/4, it is going to be A by 4, B by 4, C by 4. So, we can just remove the A, B and C and just write the fractional coordinates. Then the fractional coordinates are simply 1/4, 1/4, 1/4. So, this becomes the motif for this structure. Now, very often this structure is loosely, in fact not this structure, it is loosely called as a diamond cubic lattice, which is so often used. But there is no such lattice in the list of Bravais lattices. So, again we should avoid using this terminology. This is an incorrect terminology. If at all you have to use such a terminology, you can say a diamond structure, which is basically how the atoms are arranged. But there is no such thing as a diamond cubic lattice, but there is the face centered cubic lattice. So, diamond structure is based on the face centered cubic lattice, and we should not use this nomenclature diamond cubic lattice